Hello. In this video, I want to introduce some of the core concepts we'll be talking about this year, what an electrical circuit is, and then the concepts of voltage, current, and resistance, which are all related to each other and that we'll use again and again almost every day the entire semester. So I've got this little picture here and I want to talk about it, but I want to define what an electrical circuit is first. So an electrical circuit is just a closed loop, usually of wire, through which charge can move. So a closed loop through which charge can move. We could probably make that definition more complicated, but I think that's sufficient, pretty straightforward. This is an example on the left of a closed loop. Just as if you imagine this as a wire, so I've drawn a wire and then on the inside of the wire, this loop of wire, there are electrons. Usually when we talk about electricity, we talk about we mean electrons moving through a wire. And here's an example of that happening. So I've got a closed loop. It's important that it's closed, and I'll explain why in a sec. But if you imagine that I were to push on this electron somehow, we'll talk about ways to do that. But imagine that I were to take this electron and move it this way. That electron will then push on this electron, which will then push on this electron, which will then push on this electron, which will then push on this electron, and so on, until all the electrons are kind of moving around clockwise in the loop. So that's an example of current flowing in this electrical circuit. Notice that this wouldn't work if the loop wasn't closed. So if I had something where there was a break in my loop and it wasn't a full loop, it was just kind of almost a loop, but with a break in it so that there's just kind of like nothing in this little space. If I start pushing on, if I push on this electron again, which pushes on the next one, which pushes on the next one, there's nowhere for these electrons to go. They might get shoved a little bit further along and get sort of piled up at this end, but they can't cross the gap. They're not transitioning across the gap. In some cases they could, and that's kind of what static electricity is. But in general, you can't have charges leaping across gaps. You need a full connected wire in order for electricity to be flowing. So in this case, this would kind of be an open circuit, and we wouldn't get any flow of charge here. So when we talk about electrical circuits, we always talk about closed circuits. So let me close it back up to make it a complete loop. Okay, a few things I want to define here. I mentioned in my discussion there of circuits current. And current, and now I'm going to denote it with a symbol. We'll often see current denoted with the symbol I for reasons that are, who knows. Current is a measure of how charge is flowing in a circuit. So a measure of how charge flows in a circuit. An example of that would be the speed of these electrons as they move. That will partially determine the current. The faster they're moving, the more current there is. But also not just the speed, also the density. So kind of how densely packed the electrons are. How many of them are moving through any given spot in the wire at a given time, that will also increase the current. So more density in the charges that are moving and more speed in the charges that are moving, that will increase the current. But in general, it's a measure of how the charges are moving in the circuit. More current means there's more charge moving per time. Okay, so the next thing I want to define is voltage. And this is represented by a V, more intuitively. And voltage is a measure of potential energy which can be either supplied, say, by a battery, for example. So, for example, by a battery, or used up, for example, by a resistor, which is something that is difficult for a charge to move across. Voltage is the thing that causes current. So for example, if I imagine putting a battery into my closed circuit, so let me make a space for a battery. Let me draw it. So let's say I'm drawing in a battery right here. This is a battery. So let's say this is the positive side of the battery and this is the negative side of the battery. The batteries often come rated by their voltage. So maybe this is a 9-volt battery. What that means is there's 9 volts of potential to be used by these electrons in this circuit. So on one side of the battery is higher potential energy, and on the other side of the circuit is lower potential energy. And along the way, that potential energy gets used up, and I'll give you an example of how that works here shortly. But a battery's function is basically to push the charges in a circuit. So you plug this battery into your circuit, and now all of a sudden the charges start moving. The electrons here will move away from the negative terminal because the negative charge is repelled from the negative terminal. And the electrons will flow away from the negative terminal in this example towards the positive terminal, excuse me, because a negative charge is attracted to positive terminal. However, the current in this case is defined to be a motion of positive charge, which is a bit confusing because the charge carriers are typically electrons. But in this case, the current will flow clockwise, opposite the charge, the charge's actual motion, because the charges are negative. So current is defined to be how positive charge is moving, which in this case is opposite to the way the negative charges are moving, which is a bit confusing. But we have Ben Franklin to thank for that, because he didn't know that there were electrons when he defined how this worked. Okay, so a battery can supply potential energy to charge and get them to start moving in a circuit, cause current to flow. The last thing I want to define here is resistance, denoted by the symbol R, usually. And this is a measure, whoops, let me do that in black. A measure of opposition to current flow. A resistor is something that takes potential energy to push charge across. In fact, every wire has resistance. It takes something to move charges in any wire, even in a conductor like copper, which is what we typically use for wires. The resistance of a copper wire is very low, but there are devices that will plug into our circuits called resistors, and their purpose is to resist the flow of current. And we'll talk about why that might be useful in certain contexts. An example of how that would work here would be, let me plug in a resistor up here. And I'm just going to draw it like this as another kind of box resistor. And current still flows here. If I have a battery in this circuit and I have a resistor in the circuit, current will flow, but the bigger this resistor gets, the less current will flow in the circuit. So I can, depending on the material that this resistor is made out of its shape, and its size, I can change how much resistance this creates for the charge flowing in the circuit. A small resistance here would mean larger current flow, and a large resistance here would mean small current flow. So those are inversely related to each other. And in fact, the way that all these quantities are related to each other is through something called Ohm's law. And let me write that down. So Ohm's law is this relationship between voltage, current, and resistance in a circuit. The voltage supplied is equal to the current that flows times the resistance. In this context, in the context of the circuit that I've drawn here, the way to interpret what that means is if I have some voltage V supplied by this battery, then I will get some amount of current I based on the value of the resistance R I have up here. So if I have more resistance, I get less current for the same battery. An example of that is, I already gave this example of a 9-volt battery. I can give an example here for resistance as well. Oops. So if I had a resistance that was equal to 10 ohms, and ohms is the unit of resistance. This symbol right here, that's an ohm, ohm, Greek letter. If I had a 10 ohm resistance, we can work out how much current there would be in this circuit. So in this case, we would say there's 9 volts for this circuit is equal to the current times the amount of resistance there is. So the current here would be I equals 0.9, and the units for current are amps. So we would get 0.9 amps of current in this circuit, just in this particular example that I'm using. Ohm's law works for certain electrical components that are called resistors. It won't work in every context. And as we go on this year, we'll talk about the context where it's not really applicable. But for us right now, it's going to be really important. And we're going to use it to analyze circuits, to predict how much current flows in circuits. And yeah, it's going to be really useful. So this is a real quick introduction to what a circuit is, what's happening inside of a circuit, and current, voltage, and resistance. Bring questions to class, and I'll see you soon. Bye.